Subject that we discussed today is nonlinear propagation. If you recall, last time we discussed losses, we discussed chromatic dispersion, and these are the two propagation effects that we observe in the linear regime. And we'll dedicate this meeting to nonlinear propagation. Effects, and this is likely to continue next week as well. So the whole subject of nonlinear optics is broad and fundamental. It is so much so that we dedicate an entire class next semester with 3 lecture hours every week, almost 40 hours to nonlinear optics. And obviously I will not touch on this broad scope today. The purpose of our discussion is much more specific to address certain manifestations of nonlinear optical propagation in the silicon waveguides. Nevertheless, I will dedicate something like 5-10 minutes to an overview and some framework for this discussion, after which we'll get back down to earth and back down to the details. So the wave equation we solved to obtain the modes and all is a linear one. And this begins very early on in our derivations, because the wave equation represents Maxwell's equations in our discussions. And Maxwell equations, in essence, quantify how light and matter, or how radiation and matter interact. And more specifically, I refer to the dipole moment that develops in a material once a wave is going through it. If you recall, the dipole moment represents the response of material electrons to the field, to electrical field E. And the electrons move about and they are affected by the field, and this effect in return then comes back at the field itself, and this is in a nutshell the story of Maxwell's equations. And it is customary to assume we have, in most of our studies to date, in undergraduate and in most of your experience in optics, we assume a linear relation between polarization and field. Something like polarization vector is simply proportional to the field vector. And we take this to be absolutely true ever since the first year of undergraduate studies. But as a matter of fact, this is not always the case. More completely or more precisely would be to say that polarization depends on the field in a much more general way. It is a much more complicated function of the field vector, and in many cases we do not even know how to specify it or how to describe it in full. And when we have no better description, we often resort to a Taylor series expansion of polarization. So we approximate the polarization that we do not know as a first order term and a second order term and a third order term, and so on and so forth. And I know that I put down here powers of vectors, and it's a legitimate question what that is. These would be tensors, but I want to avoid that part of the discussion for the moment. And we have chi 1, 2, 3 representing susceptibilities of the medium in first, second, third orders, and so on and so forth. Of course, the first term in the expansion, this is the linear polarization developing in the medium, whereas all other terms collectively, the second, the third, and whatever else follows, are nonlinear functions of the field. And if we do take these terms into consideration, then Maxwell's equations are no longer linear, and the wave equations that we derive out of Maxwell equations will be nonlinear as well. We can collectively call these terms, these will be polarization nonlinear. So second and third and whatever else comes are collectively nonlinear polarization terms. So when we consider this P nonlinear, the wave equation itself becomes nonlinear. If I were to write down the wave equation, in this case, it will be something like this. It will assume the following form. This is the spatial derivatives operation over the field vector, and here we have refractive index square, c square, and the second temporal derivatives of the field vector. And this, in the linear case, should equal 0, right? What you have here on the left-hand side is the wave equation as we know it. However, when P nonlinear exists and has to be taken into consideration, the right-hand side is no longer 0, and we have something else. Here we have 1 over epsilon 0 c squared, the second temporal derivative of this P nonlinear. And because P nonlinear is at least second power of the field, if not worse, then the equation is obviously becoming a nonlinear one. And there's a lot that can be said about this and will be said about this next semester, but let me just bring you with some of the consequences. When this is a linear equation, then there is no longer transfer function. The whole concept of having a frequency response, h of omega, is a concept of linear systems. It is irrelevant to systems such as this. Put in other words, the harmonic functions E, J, omega t, they are no longer eigenfunctions of the system. Now, we are so used to it that it's a little bit counterintuitive and difficult to let go of this concept, but in most of your experience and in most of your studies, you think of a harmonic function like this, and you launch it into the system, you take it for granted that it remains harmonic. If I'm sending a certain frequency, E times j omega t, I'm guaranteed that the output would also be E times j omega t multiplied by some constant. And the temporal dependence will remain harmonic. This is only true in linear systems. In a nonlinear situation like this, when you send a harmonic function in, if you launch monochromatic light, all bets are off. You can't really tell what's going to happen. And also, so the propagation of a field component, something like this, depends on circumstances. Is it weak? Is it strong? Light at the same frequency will emerge very differently depending on power. It also depends if it has neighbors. In a linear system, the propagation of this field stays the same. It has a response, and this field will undergo the same response, no matter if there are 10 or 1,000 or 1,000,000 other components involved. Each one assumes its own transfer function. Not true here. The propagation of every given component is very much dependent on whatever else is present. And because a Taylor series expansion becomes more and more relevant as we increase power, then you can obviously recognize that these nonlinear terms, P nonlinear, become increasingly important when we raise the field magnitude. Important for strong fields. If I want to say this technically, I will speak of high intensity. And intensity is measured in watts per area, squared meter or squared microns or whatnot. So all of a sudden, if I launch weak light into a waveguide, it will come out a certain way. But if I'm raising the power and send the same kind of frequency into the same sort of waveguide, but raise the power more and more higher, propagation will become very different. And this is sometimes disturbing, sometimes an opportunity, but always has to be taken into consideration. And if this wave equation now has this awkward right-hand side, then at least to begin with, all the solutions that we worked so hard to obtain in terms of modes and propagation constants and everything else that we know no longer hold. So modal solutions no longer hold. This is very unfortunate because until this part of the discussion, we could consider some kind of a light wave going in, decompose it to its Fourier contents, spectral contents, propagate each and every one according to beta, according to alpha, and then reassemble all these components at the output if we really want to, and have a very proven and simple and easy protocol to propagate any kind of light wave. Now, we have to let go of all of this. So what do? We must offer something in return. So the alternative description for the propagation of light must be somehow put forward. So, until now, we could speak of A in of omega with frequency. Let's just think of a single component, and this will be our waveguide. And we knew that at the out we'll have the same A in with losses and with propagation of phase. And the entire effect of Z will be in the phase and losses, but not here. The magnitude I'm sending was supposed to be the same, with propagation that is only in the phase and losses that are the same, for all omegas. Now, what do? And the unfortunate reality is that we cannot propagate the optical wave from input to the output in any single jump. We cannot propagate the optical field directly from input to output. Not in time. Well, we could not do that in the time domain with a linear system already, but also not in frequency. Not in time. We cannot formulate the envelope A of T and Z, but also not in frequency. Even that is impossible. Previously, in the linear regime, I could tell you exactly how the field emerges. At least in frequency domain, not anymore. The only thing we can be sure of is differential advances. So we cannot possibly give an analytic expression for the output field in any space, not time, not frequency, and no other miracle. And the only point of view that we can actually extend to a nonlinear regime is the local, differential one. The only perspective we can extend to include nonlinearities is in terms of deltas, differentials. Is the local, and when I say that, I mean as in differential equations point of view. So I will now take the transfer function that I know and convert it or replace it to a local perspective, differential point of view, and we'll try and to extend that kind of approach to also include nonlinearities. So let me copy this again for you. A of omega and z equals A of omega and z equals 0 with so many losses and so many phases, and I will now take the beta 2, we discussed it last week. I will be representing the propagation constant in terms of the chromatic dispersion term beta 2. We have this. Let's differentiate with respect to z. So d over dz of A in frequency domain, taking this derivative is not a big deal. We'll have here minus alpha 2 times A itself, right? We'll take this factor, multiply the field component in frequency and z, plus j beta 2 delta omega squared multiplying the same thing. And this is a differential description of the field envelope in the frequency domain. Now, the nonlinearities operate directly in time, as I showed you. So because the frequency domain does not give me any special value anymore, it is no longer eigenfunctions, I'm letting go of it, I will try to move instead to a temporal description. So instead of operating on A of omega and z, I will look to formulate the equation in terms of t and z. So this is what I really need. D to the z of A as it is expressed with time, sorry, not frequency, no, with time and z. So let's convert, let's take the Fourier transform, if you will, of both sides here. This first bit is quite easy because this is just a number. I'm assuming losses that are the same for all frequencies, so I can very simply put here minus alpha half A of time and z. This is a bit more tricky, but if you recall your Fourier transform properties, you may recall that the product j omega is equivalent to temporal derivative. So if I have a multiplication factor delta omega squared, it is related, what is written here is related in the time domain to the second temporal derivatives, and there will be some j's involved, but all in all this will be minus j beta 2 half second temporal derivative of A. So what I did up to this point seems like a big step backwards, because we had this beautiful formalism to jump across the entire waveguide in one leap, and I replaced it by this tedious and inconvenient differential formalism that only takes me through one delta z at a time. So, and indeed, if we operate in the linear state of things, in the linear regime, it is much more convenient to do this. But while this perspective of the frequency response cannot be extended to non-linearities in any way or form, this local point of view can be extended to include other effects. Here we are able to introduce linearities locally in an efficient way. So from this point onwards, if we are in the nonlinear regime of propagation and I'm looking to propagate my input field, I must integrate over equations of this shape and form with all sorts of extra terms that represent the specific nonlinearity in question. So that's more or less the end of my overview, and I will start now to become more specific and address certain ways or certain phenomena that make propagation nonlinear.
Can you explain again why the second form is able to produce the
I cannot explain again because I did not explain even once why this is possible. It's something that will have to believe me. A full derivation of this really belongs in a different class, because it takes time and it takes a broader scope. And after all, here we are interested in what happens in silicon waveguides, which is a very small fraction of the entire possibilities of nonlinear optics. I just deleted the nonlinear wave equation that was here. And formally, if I put in exactly what is P nonlinear, the equation can be reduced to this. But again, this belongs in different discussions. So based on the tools that I gave you so far, you just have to believe me that this is possible. I'll try to convince you by ways of example. I'm about to give a specific example in the next 15 minutes or so of how we're doing this. It's not a proof, it's an illustration, but in any event, this is hopeless. When the system is no longer linear, there is no transfer function, there is no value in the frequency domain, and a frequency response like this is just doesn't help. I must do something else. So one of the ways and one of the conditions in which nonlinearities occur is called nonlinear index. Why does this happen? Let's consider an atom, a very naive, simplistic atom with a nucleus and an electron around it. And I know that what I'm about to draw now is not justified in any model since the 18th century, but let us assume a mental picture of an electron which is somehow distributed symmetrically about this nucleus. So overall there is neutrality and there is no dipole moment. And now, all of a sudden, a field arrives. This will be my electrical field E, and it is oscillating. It is oscillating 200,000 billion times per second because it's light. And this atom of ours sees a positive and a negative fields alternating very, very quickly. Now, a field draws the electron. When the field is positive, the electron is somewhat pulled upwards, like this. This is when E happens to be positive in a given instance, but 5 femtoseconds later, the same field will become negative, and the electron will be repelled away to here. This will be the picture at those instances when E is negative. Of course, the electron is not pulled apart because the nucleus is exerting a restoring force, but, well, it can be torn apart, but I'm assuming the field is not large enough to do that. So the average position of the electron is oscillating up and down. And come to think of it, this is exactly the dipole moment that gets into Maxwell equations. We have a positive dipole moment when the electron is being pulled up, at none, and then a negative, and so on and so forth. So this position oscillation that I just illustrated to you signifies a dipole moment that is oscillating as well. But how exactly? We're used to assume that when the field goes up and down, the dipole moment is following. But in fact, no one can guarantee that this will be a simple relation. How are these two related? It really depends on what sorts of restoring force is applied by the nucleus. If the restoring force is one of a simple spring, what we get is harmonic oscillation at omega. We get dipole moment at the same omega of our field. But this is not necessarily so. Even a spring of your daily life experience, if you pull it hard enough, well, it will break at some point, but even before that, if you pull it hard enough, the restoring force will become more complicated. It will no longer follow the simple Hooke law or stiffness law, or we may encounter regimes in which the restoring force become a more complicated function of displacement. Okay, it will be a simple restoring force here, but not anymore if I pull it hard enough. So for large displacement, as I showed you here, that is to say, large field, the restoring force is more complicated. This is a pretty big deal, because I just illustrated or tried to tell you in this cartoon that the dipole moment is nonlinear with E. But we expect normally the picture is that the dipole moment is simply related to E. This is the susceptibility of first order. And if you recall your electromagnetism for undergrad, there is something called the dielectric constant, which is 1 plus first order susceptibility. And there is something called the refractive index, which is defined by the electric constant. So if this guy fails, and we can no longer describe polarization in terms of this chi1 of this simple linear susceptibility, then our whole point of view of the index collapses. Now, index n is not a constant anymore. Instead, it is some function that is changing with the field magnitude. N changes with field magnitude, which is a bit of a problem. And the index can change with field in all sorts of functional dependencies. It can be a second order effect, it can be a third order effect, but in most media, the net result of this behavior will be an index that scales with intensity. Again, here I made a leap across some gap that I'm not willing to prove just now for lack of time, but given the necessary 2 hours next semester, I can convince you that if this medium is symmetric, the response will be the one that I'm about to show you. N will be its normal value, quote unquote, with a correction that scales with intensity. This is intensity in watts per meter square.
Usually that is watts per centimeter square.
Yeah, it depends on your scale. Well, the unit, it's a...
Generally, when we talk about the power is like, intensity is like watt per centimeter square.
The intensity is watt per area. Now, how you measure the area in centimeter squares or inches square or micron square, it's up to you. I got this comment from a reviewer on a paper that's a few weeks ago. So he says a centimeter is, and he was right actually, that centimeter is only an abbreviation to saying 0.01. The unit is length. So what I'm signifying here is that the unit here is area. Now you can go and measure the area in any scale that you like, but the functional or the general statement is what matters. I agree that if you want to give numbers, many papers will give them in watt per centimeter squares or watt per micron squared, depending on what is convenient. But the natural, like MKS kind of way, will be to use meters. But again, this is not fundamental. And of course, in order to maintain the units of this expression, this number here must be in units of meters over watt, which is the inverse. So the product retains the dimensionless quantity of index, and this number here is called the nonlinear index. It tells us just how strongly the refractive index of a medium will change with intensity. So you already see, for a weak signal, we can expect a certain intensity, the one that we're familiar with from earlier experiences. But as we crank up the intensity, this index is going to change. And this is that doesn't close too well. Sorry. So this is a microscopic or nanoscopic observation that I can get by the analysis of these dipoles. Again, I did not really do it, so don't expect to jump from here to here on your own based on what I told you, because I did not tell you nearly enough, but it's just to illustrate what sorts of consideration would lead to this. But I will now want to go back to here. And how exactly can we extend the propagation and take this into account? So let's recall the role that is played by index. Index in general, refractive index, governs how phase accumulates. Okay, we have phase E to the power of j, k something, k0, index z. If we take a plane wave, any wave in a linear medium, this is how phase gets picked up, or you can call this beta if you want. K0n will be our beta. But now I will consider the fact that n is no longer a number. So I will expand this. K0, N0, Z, and this will be the term for the linear case, and there will be something else. K0, N2 times I, Z. And that first part, the linear part of things, is in principle, I can safely assume that this is already included. Because how this index changes, well, it's a complex function of frequency. It has a beta 0, it has a beta 1, it has a beta 2, and we already took care of all of that. We eliminated beta 0 because we don't mind, it's a constant. We eliminated beta 1 because it is just a delay and we don't care, and beta 2 is already here, so I do not have to worry about any of that. But if I now go ahead and differentiate with respect to z, I will get another term on top of everything else we already had, that is because of the nonlinear index. We'll keep just this. In derivative with respect to z now brings an extra term, something like this, j k0 n2 I times whatever. So d over dz includes all that we had before, linear losses, chromatic dispersion, and something else. And that's the something else. So dA dz, and I will no longer write t and z everywhere, will accept that the envelope of the pulse changes with time and position, has a term for linear losses, and has a term for chromatic dispersion. And now it's got something extra. Plus j k0 n2 times I. What is I? It's power divided by area. So I will put now here in the denominator, this will be the area of the model course section, so many microns by so many microns, and it's power divided by area, and we agreed last week, I hope you remember, that the field A is scaled so that A squared is power. This is actually power. And this extra term here is the nonlinear term in the propagation equation.
How did the area, the area is model area?
It's the modal area. It's not the physical area of the core. It can be calculated based on the field profile. There are some recipes, but let's just keep it intuitively area. And this coefficient here is called gamma, without the j. Everything else here, we have a name for it. This is called gamma. This is the nonlinear coefficient. And as you see, this nonlinear coefficient like many similar cases, is a measure of medium and geometry. It is affected by N2, which is a material characteristic. It is affected by area, which is our design in geometry. And by K0, that is to say, which wavelengths we decide to launch in. So it is not strictly a property of just the material or just the waveguide, it is a property of the problem, taking into consideration which light wave we're sending in and which geometry we fabricated and what materials make it up. Units. Let's look again. We have K0 is 1 over meter. N2 is meter square over watts. And effective area is another area in the denominator. So these cancel out. So that the units of gamma are 1 over power times length. Again, you'll be right to say, is this kilometer, meter, centimeter? It really depends on the medium and the sorts of conditions we're in. But in terms of the generic scale, it is reciprocal to power and length. So now our task becomes solving this equation. I'll just delete some of the clutter around it and write it up in the final, more concise form. And if we ask ourselves, how is the light field propagating, the problem becomes solving this equation. must say that I cheated you in so many ways here that I cannot even begin to track them all. This is not a rigorous argument. I reached this equation through a sequence of hand-waving arguments that involved a good number of lies, but this is only for the sake of time. I'm trying to illustrate to you why this is true, but this argument does not replace a fair and true derivation, which is simply done elsewhere. But the argument does give some kind of intuition, and maybe I could walk you with me part of the way, but there's a good bunch of contradictions and inconsistencies in reaching it the way I did, but this just serves to guide your perspective on intuition, and intuition on why things happen the way they do. So we end up with this. dA dz equals minus alpha half of A, j beta 2 second temporal derivative, plus this beautiful thing, j gamma power times A. And this equation has a name. Well, it's the nonlinear well enough. You see here the third power of the field, so this is no surprise. It's an equation. Again, no big surprise. And the name is Schrödinger. Nonlinear Schrödinger equation, or for short, NLSE. Why the name? Because the form that we achieved is the exact same mathematical form of an equation that comes up many times in quantum mechanics. So you should not be overly afraid of the name. There is nothing quantum about the discussion that we're going to hold, but the mathematical form of the equation that we reached is identical to the Schrödinger equation that shows up in quantum mechanics, and we need to solve it. How do we solve it? Unfortunately, we have no analytic solution for the general case. We can only obtain analytic solution for a limited set of specific initial conditions. I will address few of those in the remainder of our discussion, but in almost all scenarios, you'll have to go down to your MATLAB or any other favorite numerical platform and integrate this step by step in time and position and obtain a numerical solution. We have only specific cases in which analytic solutions are available. And I will again dedicate some time to few of these cases, also because of their didactic value, because these may be sterile or unrealistic in various respects scenarios do teach us something about the character of the problem. So one case that we can solve for is if chromatic dispersion is very weak. In case beta 2 is negligible. Okay, it's never completely true, because we always have some extent of chromatic dispersion. However, in some problems, the chromatic dispersion is comparatively small, or alternatively, we worry about a narrow range of frequencies so that it does not come into play very strongly, and we can approximately address propagation without it. So, in these sorts of cases, then approximately dA dz includes only linear losses and nonlinearity. And this can be solved. I'll go over there so you can see me better. So the solution we are able to obtain is in the following form. A is a function of position and time. Will follow the temporal shape that we started with at the input, z equals 0. It will also exhibit linear losses, but in addition, it will also pick up an extra phase due to nonlinearity, which is a function of position. This will be an extra phase due to nonlinearities. Now, what is it exactly? The nonlinear phase is given by gamma times the input power at every instance, so this is input power, times, well, what do we need here now? Length. This is inverse watt length. We've multiplied by watts, so we now end up with an expression that measures in inverse length. We should have some length factor here, and we actually do. This is called the effective length. Okay, what is the effective length? So let's specify that as well. If I take it one step further, it's gamma input power, and the effective length is given by 1 minus this exponential divided by alpha. Let's dwell on this for a minute. Well, just so I know how to scale myself. How many of you have seen this before in any shape or context? I know you did. Karen, I believe also, if I recall your master's training, and who was your advisor. So you saw this as well. And for the other, this is completely out of nowhere. Am I right? So how do I convince myself with such a thing?
Where the term has come actually. This for what? Related to effective length of what?
It is the effective length of propagation in the waveguide. I will explain. So let's put this all together. We have input multiplied by this and multiplied by this. And here we have in the exponential this marvelous expression. One way to convince yourself that this is true is put it in the equation. If you actually try to differentiate this, you will find that the equation is satisfied. So in retrospect, if I put it in your face and you want to validate that this is true, it's pretty technical and you can do it. But what does it signify? Let's start with the effective length. And I want to examine two limiting cases. The first case is one of a very short waveguide. Z approaching 0. Let me get back here. In a very short waveguide, I'm able to approximate this exponential by the 0 and first order terms. This is approximately 1 minus alpha z. And what we have very quickly is that L effective in this case approaches, z. So for very short reaches, effective length is just physical length. So effective length equals physical length. It's all very nice. The other limiting case I wanted to dwell on for a moment is one of a very long waveguide. That is to say, z approaches infinity. And at that limit, this exponential just goes away, and the effective length approaches 1 over alpha as an asymptotic value. I can take this one step further, and if I were to draw this somehow, let me now delete a bit more. If this axis will be my physical length, and this is the effective length, then initially they are one and the same. But soon enough, the effective length levels off at this asymptotic value of 1 over alpha and deviates away from this initial linear relation. So we've clarified maybe, at least in part, what that is, and what this entire expression tells us, that the phase of the waveform scales with power, and that phase scales somehow with length. Let me address the power thing first. I'm drawing now input power as a function of time. Let's say I have a pulse. If I were to draw the output power, and remember, power to us is magnitude squared. What's going to happen? Power, not so much. If I now were to take the magnitude squared of this little thing, all the phase will be taken out of it. Right? Take absolute square, phase doesn't matter anymore. And we do see losses, but not much else. The output power will exhibit some kind of losses, but will retain its shape. Let me show you another plot. Let's draw the instantaneous phase, beginning with input phase, and let us assume that I'm sending a real valued pulse. So the input phase is level here, 0. But if I look somehow at the output phase, what's going to happen? It is no longer fixed. Now, as I go along the pulse, these center regions are more intense. Okay? Because they are more intense, remember this. So these more intense parts of my signal see, in essence, a different index. So they pick up extra phase. In contrast, the edges, leading and trailing edges of this pulse are weak. And because they're weak, they see the normal index. So they pick up lesser phase. And we don't even need to resort to this because this is in our face here. Nonlinear phase follows power. So now all of a sudden, if I had some kind of a phase meter, it's not very simple to do, but at least conceptually, if this is now my output phase, then it is varying within the pulse. And how so? The phase these phase variations scaled with power. So the effect that I just described to you is called phase modulation. It's now easy to see why. The phase of the wavefront is being altered, it's being modulated within the extent of the pulse, and this modulation is because of the power of the very same wavefront. It's not just changing, it's changing because it is intense. The variation in power of a pulse modify its own instantaneous phase profile. This is why the behavior is referred to as self-phase modulation. Or the younger students would call it selfie modulation. And this is, in acronym, it's SPM. And you mentioned the broadening, which is very important, and this is exactly my next part of the discussion.
So input power shape does not change?
Input power shape does not change, because if you take the power is this, it's A squared. And when you take the square, the magnitude squared, phase information is gone. So if you conduct a simple detection experiment, you do not even know this happened. You can see the losses all right, but a straightforward measurement of power on an oscilloscope will not show you this. Nevertheless, it is there, behind the scenes. The phase that you do not see in your detection is varying all the time. But this always comes back at us. If something like this happens, we always pay the penalty. And let's now, do you still see me out here? I hope you do, because I need the rest of the board now. Let me describe to you one last experiment, and this will be spectrum at the input. What is spectrum? If I take my A of t at the input, go to A of omega at the input, and take the magnitude square. If this is the observation of an oscilloscope, I will now draw to you the observation of a spectrum analyzer. Between these two instruments, you cover 90-something% of all measurements we take. The spectrum analyzer just goes one frequency at a time and tells you how much power lies at that frequency. So if take my input pulse, I can make a Fourier transform, say it's a Gaussian, so even in Fourier domain it's a Gaussian still, and I get some kind of form. Now what? In the output, does it stay the same? Fortunately, no. It broadens. And we need to spend a moment on this. If you had some training in signals and systems and Fouriers and so on, you're accustomed to think of this temporal width and this spectral width as being related, right? If a pulse is short in time, it occupies a broad spectrum. If a pulse is narrow in spectrum, it is broad in time. And the two are somehow inversely related. But this is a very strange situation. The temporal width is unaffected. We've seen a loss, but the shape is still the same. Nevertheless, the spectral width has changed for the worse. Maybe it depends if it's better or worse. I don't want to take a stand. It's broadened. How is this possible? The reason is here. The signal after SPM is complex. It's no longer real valued. The relation you came to expect and the relation you came to take for granted between time width, frequency width, they hold for real valued signals. When they are no longer real valued, such as here, all bets are off. So if I were to summarize this, temporal width of A squared, the same. Spectral width of A at the same time is broadened. Why? Because of the phase. And this broadening is one of the clear-cut signatures of nonlinear behavior, because, for instance, it lets you introduce components you never had at the input. In a linear system, you have h of omega. So you have some spectral content, multiply by h, you get the output. Suppose you had 0 at the input. Then no matter what is your medium, you get 0 in the output. You multiply 0 by whatever, you still have 0. Not true here. In this SPM regime, we are able to generate spectral contents when we never had anything. And because of the nonlinearity. So I told you something, hopefully, about the scaling with power. And the next thing I want to address is the length, and try to rationalize to you why the effective length behaves the way it does. So we go into the waveguide. First, I don't know, millimeter. Power is huge. So we're picking up phase very drastically. Power is high, index is very high because of that, and the phases are accumulated. But the same millimeter also brings losses. So when we enter millimeter number 2, the power is a little bit weaker. So how much phase we're going to pick up at millimeter number 2? Yes. A little bit less, because we are now using lower power. Go to number 3, the power is lower still. And so on and so forth. So this actually tells us that the addition, the increment to this phase modulation is getting less and less. Because we're losing power, the contribution of the first millimeter is the largest, and the contribution of the second is less, and the third one even less, and so on and so forth, until we get far enough inside that the power is now very low. So then these next millimeters, another and another and another, give us very little extra phase, because power is now weak, until eventually it levels off. And the effective length appears in the solution in the way that it does, because it represents this decaying increment, or this slower and slower and weaker contribution to the nonlinear phase as we keep on losing power. So maybe if you think about the situation in these terms, you can rationalize to yourself why the effective length looks the way it does, at least qualitatively. So this much for SPM. Questions? Okay, it will get even more awkward next. Let us address a slightly more complicated situation when we have a waveguide here. And at the input, we have field 1 at omega 1, e to j omega 1t, with a1 here, and this one will be intense. So we can already expect that at the output, A1 undergoes some sort of SPM. Let us now assume that in parallel, we also have a second field. Field 2 at omega 2. However, A2 is weak, which means if this second field was alone in the waveguide, it should come out subject to linear propagation alone. So if A2 was alone, we might expect linear propagation alone. And since we are still within the specific case of no chromatic dispersion, this is pretty simple. Why? Because I'm still within the restrictive case of no beta 2, so if this field is on its own, no worries. It just, you put in the losses and you know what comes out. And my question now becomes, since it is not alone, what's going to happen? And partially, it's getting there, but in the linear sense in the linear world, this is a very stupid question. Because in a linear system, these two signals do not even know about each other. This one will get response 1, this one will get response 2, and if you bring the other one out or in and make it weaker or stronger, the second one doesn't care. So the question has no meaning in a linear system, but it becomes very relevant in a nonlinear regime, and you may guess that A2 undergoes phase modulation as well. Even though it is weak, even though it is not intense enough to introduce nonlinearities on its own account, it does suffer or does benefit or does feel the nonlinearities that the other guy brings upon. Without mathematics even, I hope I can convince you. Recall again, N2, N equals N0 plus N2I, and I here stands for overall intensity. Overall intensity of this one and this one. So once I have an intense waveform in the picture, intensity is already high. So this is not N0 because of A1 already. That is enough. So the propagation of that second field is not following N0, because this is not what you have in a waveguide, it follows this. And this means, I will write it down, propagation of A2 is no longer according to N0. It includes nonlinear effects that come from this.
So A1 and A2 does not follow the same N0?
Neither one follows N0. A1 obviously follows a different index than N0. Even if it was just alone, if it's intense enough, then yes, it sees a different index. But what is more outrageous or more surprising, that even this weak little guy now sees a modified index because of the neighbor. The presence of A1 is enough to alter the medium in such a way that all other waves present see the results. Okay? A2 alone cannot raise this, it's too weak. But it is propagating in a medium that also sees A1, and because it sees A1 and A1 is intense, the medium is modified. And the effect will be felt across the board on A2 as well. I can tell you exactly how. Not in this respect. It does matter when we go on and consider even more bizarre observations like the introduction of omega-3 and omega-4. Then it matters big time, but for the sake of this discussion, not so much. Because I artificially eliminated beta-2, it doesn't matter anymore. If there is no chromatic dispersion, then in principle, it doesn't matter which frequencies. In the real world, when we do have chromatic dispersion, then yes, it can make a difference. But I'm bringing this one step at a time because this is awkward enough if you're not used to it or haven't seen it before. So now, strangely enough, if I write A2 at the output, it follows A2 at the input with the nonlinear losses, but it also have a nonlinear phase, which is not even its own fault. It sees A1 of the input power times effective length. So you see this? The power of wave 1 changes the index, as we've already discussed. Therefore, the power of wave 1 is changing the phase of wave 2. So yet again, this is phase modulation taking place. But now it is not self-phase modulation anymore, because what we're seeing is the power of one wave affecting another. So this is called cross-phase modulation. And no, it's not CPM, it's XPM. Because this is how people like to note cross. So we had SPM before, self-phase modulation, now we have cross-phase modulation. And if, just to make life a little bit more annoying, there's a 2 here, which I'm not going to explain, but it's there. Again, it is discussed someplace else. So the cross-phase modulation is even twice worse than the self-phase modulation. And imagine that we had not 2 terms, but 3, 4, 10, 20, then all these cross patterns happen all along. Yes, just now. That's the next thing. So I see this is not new to you.
I studied Modulation.
Okay, so you know all that stuff. Good. So, SPM, XPM, questions? Everyone is on board. Well, let's look at something even more awkward.
It's getting worse.
It's getting worse. It is getting worse. Frequency axis, suppose I'm launching in two tones. Omega 1, omega 2. Separated by some offset, capital omega. Think of just two lasers. Each of them is ideal, monochromatic, no pulses, no modulation. So in the frequency domain, these are two deltas. And again, I apologize in advance that the discussion is not going to be rigorous. Just like the previous ones were not rigorous, but this serves to show you, to give you the broad picture. Let's write the overall field. Again, I will assume for simplicity that both these are the same magnitude, just to make life easier. So overall field will be A with frequency number 1. I'll take this omega 0 minus 1/2 of omega t. This is laser number 1. Here's my center. I call that omega 0. So one tone is half the difference to the left, the other tone is half the difference to the right. Here's 1, here's 2. What's the overall power? Well, I should take this squared. So I have from this term squared just A, and again. But I also get, if I multiply one by the conjugate of the other, or the other way around, we'll get twice A cosine of omega t. So that's my overall power. And let me examine just this for a minute. If we agree that n is n0 plus n2i, this signifies that the index is being modulated at frequency omega. So the instantaneous refractive index in this medium is n of t, has some bias value. This bias value in itself is not n0 because of these guys, but doesn't matter. But it also has a term that's twice a squared divided by effective area n2 oscillating. These don't matter, the constants. The fact that is central to the discussion, that index is being modulated. And these two tones now live in a world in which the index goes up and down. What is that going to do? This is scattering. When light, any light wave, one, the other, another one that I bring in out here, doesn't matter. When it goes in a medium where index is not constant, but the index itself is oscillating in time, what we get is scattering of light into sidebands. So some of the light in frequency omega 1 will be scattered away omega hertz to here and omega hertz to here. And this is scattering due to an oscillating index. And the same goes for this bit of light. If it also scatters somewhat, capital omega to the left and capital omega to the right. So we can expect some kind of a contribution here due to scattering of omega 2. And we can also likewise expect some contribution here overlapping due to the scattering of omega 1, but that's not the end of it, because now we have something out here and out here. We may call this, if this is omega 1 and omega 2, we sometimes use the name omega 0 and omega 3. Omega 0 is not a good name anymore, so let's just call this omega 3 and omega 4, just for the sake of giving names. And we never launched anything out here or out here. And I'm repeating this time and again because I want to take out the LTI intuition out of your heads. In a linear system, when you launch in a 0, you're guaranteed to get a 0 in the output. And this is very much not what happens here. There is no input light at omega 3 or 4, and yet we get light at the output for those frequencies. And this is a clear-cut, again, nonlinear fingerprint. And if we make an experiment such as this and measure how much scattering is appearing out here, and you measure how much power you put in, how much power you get out, it is possible to extract the nonlinear index of your medium. And this is something we did about a year ago. We characterized the waveguide from a material called gallium nitride. It's pretty important because this is what makes blue LEDs, and it was a Nobel Prize was awarded for the study of this material. Of course, it's very important for LEDs. It is not so important for nonlinearities. This is why no one looked at it. So we just had the opportunity to make exactly this experiment and retrieve the nonlinear index. So this was the first report of just how nonlinear is gallium nitride. And this is a paper from the beginning of 2018. So now we're starting to touch on things we actually do in the lab. And you use the term, of course, correctly. This effect where you're mixing between these waves and get products at a whole entirely new frequencies is called four-wave mixing, or for short, FWM. So cell phase modulation, SPM, XPM, and four-wave mixing are the three most common manifestations, and they all come from nonlinear index. They all come from the fact that the material of the index is not a single number anymore. It is a function of intensity. It is a function that changes even within the duration of the pulse. It varies instantaneously, and this causes all these things: the spectral broadening, the crosstalk between terms, the four-wave mixing, generation of these awkward satellites. These are all manifestations of SPM, and just mind you, we got all of that with no beta 2. You can start to ask yourself what sorts of complications would emerge if we look at the entire equation with beta 2 included, and I'll give you just one hint, should time permit. Not so much. I'll just start and I'll revisit this more slowly in next week. So let me give you the full equation again. dA dz, losses beta stein half, beta 2 half, day A, J, gamma. So what do we know so far? The first term here, or losses aside, this term here gives distortion. We discussed this last week. Distortion in time domain. In the way of chromatic dispersion, we had that last week. This term gives distortion in its own right. This time, this is distortion in the frequency domain, in what we have seen as SPM. And you may well expect that when we bring the two together, we get even greater complication, and some very awkward dynamics can come up. And indeed, in most boundary conditions you might invoke, this is exactly what's going to happen. But the awkward question I will ask now is, can we balance them? Can those effects cancel out? Instead of reinforcing each other, somehow eliminate each other. And that's possible. That's actually possible. If we take out the losses, suppose we have low losses, so that alpha equals 0. That's of course not strictly true, but mathematically let us assume that this happens. So I'm taking this out. It turns out that we can find very particular input shapes that will go along completely undistorted. Even though we have chromatic dispersion that is looking to break up the pulse in time, and we have SPM that is looking to break out the pulse in frequency domain, it does remain intact. So I apologize. It's the same. This guy always finds that my classes for the day the same person from Sunday. I don't know how he has this. Probably has my schedule. So for specific input shapes, we can find that A T magnitude squared to be the same for all Z. This is an outrageous behavior, because dispersion alone will change the way the pulse looks. Phase modulation alone will change how it looks. So how can we even hope to retain the form? But this is possible. Of course, this requires that we choose the input shape of the pulse very carefully. The shape that we need to use is called hyperbolic secant. So this requires very specific temporal shape at the input end. So A at Z equals 0, T cannot be just anything. It's got to be something specific, and I'll come back to this next week. And in addition, we must retain a certain relation between the temporal width of this shape and the power. So we'll be looking at something like this, a hyperbolic secant function of time with a width parameter tau and a magnitude a0, and these will have to be related in a specific way that I will tell you about next week. But so long as these are related, we can reach a regime in which nothing changes. We always have power the same. This is kind of miraculous. And pulses that observe this are called solitons. Maybe you've heard the term, and more specifically they are temporal solitons because they change with time. And they are quite unique. Just if anyone does not know, this hyperbolic secant of x is this. It's just the inverse of the hyperbolic cosine function. So this is what I mean when I put down hyperbolic secant. Okay, but how exactly these are related, I'll do that next week when everyone is more fresh. Questions, comments, complaints? Okay, so we meet normally next Tuesday. We'll begin with a brief quiz number 2, 15 minutes, and then we'll come back to these issues. Thank you, good evening.